Okay, so what are these glycols that we're talking about? So we are talking about monoethylene glycol, diethylene glycol, triethylene glycol, and tetraethylene glycol. These mixtures of glycols are used for various different things, such as polyester fibers, engine coolants, solvents, and if you're familiar with the midstream industry, TEG is famous for its dehydrating capabilities in natural gas. Since each one of these is going to be a final product that will sell in the market, we're going to be targeting about 99.9 mass fraction for each one of these components. Is there any questions so far about kind of what we're looking at or how we're going to be setting this up? And again, over all of this, what we're going to be looking at is setting these columns up to match plant data. So let's talk about the configuration. So our inlet stream is going to be a stream of mixed glycols. This is going to be the stream coming off of the reactor block. Again, the ethylene oxide reacting with excess water. That stream is then going to be dehydrated and then sent to the separation units that we're going to be looking at. What we have here is two MEG columns. So these first two columns are going to purify our monoethylene glycol. We'll then send it to our DEG column to purify our diethylene glycol, and then finally our TEG column to pull the TEG off the top with a TTEG stream in the bottom. These units are going to be operating under a vacuum. That is because the boiling points for each one of these components is relatively close to each other, so operating under vacuum will help us in that area. All right, so let's look at this inlet stream. Our inlet stream is at 290 degrees Fahrenheit, 2 psi, a good amount of flow, 230,000 pound-hour. And the composition, as I said, is going to be on a mass fraction basis. We have inlet composition is 75% MEG, 25% DEG, with a little bit of TEG and an even smaller amount of TTEG. Notice that we still have water. So that stream is going to go into our first column, the MEG unit. What this unit is going to do is it's going to get rid of any of the water that we have remaining. So our water, since it is lighter than monoethylene glycol, we'll send the water out the top with a little bit of that MEG, and we'll be pulling a side draw on stage 3 with our pure MEG, so that this is going to be our product stream. As you can see, we have 14 stages in this first column, and our feed is going to be feeding onto stage 11. The column internal, so now that we understand how many stages and such is going on, let's talk about the setup of it. So for this setup, we're going to be using an ideal stage model with a total condenser and a reboiler. The next thing that we'll want to set is the pressure drop across the column. The pressure drop for this is 0.3 psi. Once we've set the ideal stage model and the pressure drop within the column, we can start working with our specifications. The first thing I want to note is that we already have 3 specifications in this tab. We have a boil-up ratio, a reflux ratio, and a flow ratio. This is because we have set up our column to have a condenser, a reboiler, and a side draw. So these, whenever we add one of those components to the column, we'll be given a desired specification. And at the top, you can see that we have a degree of freedom of 3. The column won't be able to solve until the degrees of freedom are 0. And to reduce those numbers, we would simply change these specifications from calculations to specifications. So what I always like to do is when starting to look at another column is set the boil-up ratio, the reflux ratio, and the flow ratio all to 1. So we'll set all of those to specifications and then execute. This won't give us the right answer. This won't give us anything that we're truly trying to solve for. It just gives us a really great starting point and helps us start at a converged model. So as you can see, our column turned green, meaning we have converged the model. But as you can see, our MEG product stream is at 99.45. Obviously, that's not where we want. That's not where we want to be at. So what we can do is we can play with these boil up and reflux ratios. So let's say if we change our boil up to 10, see what happens. We get a worse MEG purity. So what we can do is we can sit here and play with these values. Or an easier way to solve a column to match plant data or around design parameters is to add different specifications. There's a lot of different types of specifications that you can add to a column. In our case, my plant data says that I want to set that side draw stream to a flow rate of 64 tons an hour. That's something that I for sure want to match. So to do that, I would set a draw rate as my specification type. And we can name this MEG draw rate. Once I've set the specification, we'll need to tell ProMax what stream we're looking at and what kind of flow rate we're talking about. So the draw stream that we're looking at is the MEG stream. And I want to set it to 64 tons an hour. So we'll set a mass flow and change the units to ton per hour with our target of 64. Once I've set this specification, I can click OK and it will appear on our specification tab. This grayed out column right here is what ProMax is calculating. So as you can see, our current draw rate is 31.7 tons an hour, but we still have 0 degrees of freedom. So what we'll have to do is we'll have to change one of these specifications, let's say the boil up ratio, and set our MEG draw. We can execute that, or we can continue to add specifications. There are still a lot of other specifications that I would like to add, so let's go ahead and do that. Another specification I'd like to set is the distillate rate. So I know that on my MEG1 column, I have a distillate rate of 5.5 tons an hour. The distillate rate is how much is the MEG1 recycle flow. So we'll add another specification. Again, it will be a draw rate, and we'll name it MEG, distillate rate. The draw stream will be the distillate. Again, in mass flow, we'll change the units to tons per hour. And our target is 5.5. Once we've set that, again, we'll remove one of our current specifications and set the new one that we'd like. Okay, so we've set how much MEG we want to be drawn out. We've set the distillate rate at the top. But now I want to ensure that the purity of my draw stream is 99.9 on a mass percent. So we'll go ahead and add one last specification. And this will be a component composition. We'll name this MEG purity. The stream that we're looking at is going to be the MEG stream. And we want the mass fraction. The component that we want to target is MEG. And we want 99.9%. Alrighty. So we'll remove that flow ratio specification and set this MEG purity. All right, so let's execute and see what happens. Perfect. So ProMax was able to solve the column matching each one of these specifications. And as you can see, our boil-up ratio was 3.3 and our reflux was 14. So those are the numbers we would have had to guess to get our desired specifications. But by setting these specifications ourselves, we are able to save a lot of time. All right, so let's look at these streams. So just to double check, this MEG stream, product stream, mass fraction basis, we have 99.9. And let's look at stream 7. So our bottom stream, we have gotten rid of most of our water, pretty much all of it, so that looks really good. Although we still have a significant amount of MEG. And we have some still DEG that we'll remove in the following columns. Let's see, Robert asked, is the convergence of the columns to specs normally that quick? It depends on what kind of specifications you're setting. Generally, we don't see anything taking longer than, I would say, maybe 30 seconds. It is relatively quick. Alrighty, so let's move on to MEG2. This is where we're going to get rid of all of the MEG. So as you can see here, our specification that we want to meet is 0.005 mass percent MEG in the bottoms. So that's our target here. Again, we'll go to our process data tab in the column, ensure that we are in ideal stage. And let's look at this pressure change within the column. In the first column, we talked about setting a pressure drop across the entire column at the top. Another thing we can do, another way to set this, is to set the top and bottom stage pressure. So we know our top stage pressure is 1.45 and our bottom stage pressure is 1.74. ProMax will then calculate each stage pressure and the pressure drop across the column. It's just another way to achieve the same thing. We'll now look at our specifications for this. Again, we will always be given a boil-up ratio and a reflux when given a condenser and a reboiler. And as always, I always set both of those to a target of 1, set them to a specification and execute. just so we can get a good starting case. Let's see. So doing so gave us an 4.4% MEG in the bottom. That's mole fraction. Let's change that to mass fraction. So on a mass fraction basis, we still have 2.6. Obviously, we need to play with the specs here to get this column to do what we want. Alrighty, so the first thing that we'll want to set is a component composition. Again, we're going to target that MEG in the bottom. All right. The stream that we're looking at is the bottom's liquid on a mass fraction basis. And we want to target 0.005. All right. Let's remove the boil up and execute that. Perfect. So we have met our spec at the bottom. So life is good. We're where we want to be. The reflux ratio that we're also looking at is 1. So we've met our specs in that column as well. All right, so now let's move on to DEG. So if we look at our stream going into that column, we have no water. We have very little monoethylene glycol. And we have a stream about 97% diethylene glycol. Again, this column is going to give us a target, or we're targeting a 99.9 mass percent of diethylene glycol in this upcoming column. So that would be a good specification. And another specification we're going to target is the diethylene glycol in the bottoms. So if you look here, we'll be setting a spec with 99.9% in the product stream and 0.03 DEG in the bottoms. Okay, so let's double click in this column. As you can see, we have 10 stages with the feed on stage 6. As always, we'll start on the process data tab, ensuring that we are in ideal stage. Again, we have a total condenser with a reboiler. We'll want to set some sort of pressure drop. So this is another way to set a pressure within a column. The first one was just doing a pressure change. The second was setting the top and bottom stage. And this third way is setting the bottom stage and putting a pressure drop. So there's multiple different ways to input pressure change within the column based on any information that you may have. We'll then move on to our specifications. Again, you see that we have 2 degrees of freedom in this tab with boil-up ratio and reflux ratio already built in. Again, these are always given to us when we have a condenser and a reboiler. I will set both of these to a specification of 1, just to turn our column green. If we were lucky, The boil-up ratio and reflux ratio of 1 would give us the answers we want, but unfortunately, we have to add some specifications. So let's see, the DEG in the bottoms currently is 96% right now, mass fraction. So that's definitely not what we want. We've got to manipulate this column to get it to do what we want. Okay, so let's start with the composition in the bottom. We know we want 0.03 weight percent of diethylene glycol on the bottom. So that would be a component composition that we're targeting. We can name this DEG bottoms. The stream that we're targeting is the bottoms liquid on a mass fraction basis. And again, we're looking at diethylene glycol with a target of 0.03. Okay. And we'll also want to set a specification for our product stream. Again, these are going to be sold to the marketplace, and we want to make sure that we have high purity products. So we'll add our product specification again as a component composition. We'll label this DEG purity. We are looking at the distillate stream on a mass fraction basis. And we want the purity of diethylene glycol to be 99.9%. Alrighty, so let's set both of those specifications and see what happens. It's yellow. So what can we do? Let's look at the values that ProMax is calculating. You can see that our DEG purity is at 98.5. So we're definitely not at 99.9. We need to work on this. And we still have a relatively high amount of DEG in the bottoms. We need to get more DEG out of the bottoms. So what is one way to decrease the amount of DEG in the stream leaving the reboiler? Okay, adding trays and stages would increase our, yeah, that could help. But let's look at our boil up ratio. It's saying our value is 105. So if we increase our boil up ratio, theoretically, we'll be boiling more and boiling harder and get more DEG out of the bottom. So as you can see, we have degrees of freedom of 0. So we cannot set that as a specification. But what we can do, it's currently calculating at 105. Let's guess 100 and set it as an estimate. So what ProMax is going to do is it's going to start at around a boil up ratio of 100 and iterate around there to see what happens. This is kind of where you have to use a little bit of that engineering background to come up with a good solution. We execute, you see it's iterating through. And that boil up ratio is actually calculating at 333, so it's quite high. But we are able to meet both of our targets. So we'll have a 0.03 DEG in the bottom with a product stream of 99.9. Okay, so now that we have solved, Oh, the first two columns. Let's talk about this third one. I accidentally solved it. Oh, okay. So we have, again, the TEG column is going to be ideal stage, total condenser with a reboiler, and our pressure drop, always make sure that you set it. We have a pressure change across the column with a top stage pressure specified. Now let's talk about our specifications. We currently have a boil up ratio and a reflux ratio set to 1. Again, this is a really great starting point. You can use your engineering intuition to see if that's truly where you want to be. Our TEG product stream is currently at 99.87, not the 99.9 that we want, so we definitely need to add a couple of specifications here. And let's see look at our TEG stream. So with a boil up and reflux ratio of 1, you can see that we still have a 94% TEG coming out the bottom. So this is not ideal. We really need to purify these two products a little better. Okay, so we can add a specification for the top. So we'll add a component composition for TEG. Stream in question is going to be the distillate. We want a mass fraction of TEG, and we're targeting 99.9. Okay. So let's move the reflux ratio and set that and see what happens. Okay, it's yellow. We're still at 99.87. We have some work to do. So let's set the bottoms purity. Another component composition. This time we're looking at TTEG in the bottoms. We want the bottoms liquid on a mass fraction, tetraethylene glycol, and let's say we want 99. Let's start low. Let's just start with 99 and see what happens. We'll remove the boil up ratio specification and set the bottoms purity specification. It's iterating through the process. Okay. So we're at 92. We're a little bit closer, but still not where we want to be. Let's see. Let's look at this bottom stream. We still have 7% TEG, so we need to increase. Let's set this to 40 and set it as an estimate. Maybe that might help. And setting the boil-up ratio to an estimate helped ProMax iterate through and properly solve this problem. So that is a really nice trick that I like to use. If you know that you're meeting a certain purity spec in the bottom and you're not able to quite hit it, but you still have product in that stream that you need to boil up, and your boil up ratio is increasing significantly, but you don't have additional degrees of freedom, the estimate is a really, really great option to choose to help you solve the column in a way that will help you meet your specifications. So that is a quick rundown of a couple of different ways to solve your columns, whether that be using to match plant data or to using design parameters. So if you have any questions regarding the column or any of the different specifications that we use. We have a couple of minutes for questions, the rest of the hour for questions. So feel free to ask or give us a call, email us. We're here to help you figure out how to better be of use to you in your specific engineering problems. But thank y'all for joining us. Definitely appreciated all of y'all's attendance and some of the questions that y'all were asking. Okay, so let's see. Mike asked, how many actual trays in your ideal stage? So right now we have a real to ideal stage ratio of 1. This is where we can change it. In some of our amine units, we'll go in and change that to 3:1, or if you have a specific column and you know the ratio, we can go ahead and manipulate that for you. Good question, Mike.